Good day, everyone. Like how we greet each other in Australia, which seems to suit the occasion perfectly, no matter where you are in the world and what time zone you might be in. I'm very thankful for the organizers and you to give me this opportunity to share with you what we have been working on recently. Let me share my screen with you. The topic I prepared today to present to you is Martensite as the key to unlock the ideal strengths in solid. My name is Yinong Liu, and together with my colleagues, we are from the University of Western Australia. So the ideal strengths, well, that is not a new topic to us, new knowledge to us, because we all know that ideal strength is a measure of the effort required to break the bonds between atoms within a solid. And the ideal strength is generally considered to be on the order of 1/10 of the Young's modulus of the solid, which corresponds to about 10% for the ideal elastic strain limit. Indeed, some people have done a theoretical analysis by means of molecular dynamics simulation and first principles calculation, in which it's predicted that the carbon will have a theoretical strength of 95 gigapascal, silicon 22 gigapascal, and germanium 14 gigapascal. And all this is because the strength of the bond between the atoms in each solid. So if that's the theoretical prediction, and here are some experimental evidences. And this is a piece of copper nanowire observed in situ under electron microscope during tensile deformation. The copper nanowire is measured to have an elastic strain of 7.2%. This is aluminum oxide nanowire. By bending and breaking it, is measured to have a strength close to 40 gigapascal and a elastic strain of 8.5%. This one shows diamond nanopillars. They are measured by breaking this way, measured in bending to have a strength of 98 gigapascal and elastic strain of 9%. So these values are tremendous, much more than what we can expect in bulk materials. However, the question is the same bond between atoms also exist in bulk materials. So in that sense, they should have at least the same potentials to achieve such extraordinary strengths and elastic strengths, but they don't. In reality, the strengths of the bulk materials are typically 5 to 10% of what is possible. And we know the reason why, because they all contain defects. So through the years, people have developed many different techniques, methods to strengthen our metals, such as solid solution strengthening, dislocation strengthening, precipitation strengthening, green boundary strengthening, twin strengthening, amorphization, even go beyond the crystalline concept and into creating amorphous bulk metals. But all these strengthening techniques seem to share one common approach and one common philosophy, that is to build up strength from bottom by restricting the activities of defects. Yet, all these techniques have their limitations. For example, solid solution strengthening, the concept of high entropy alloy represents what we can achieve, the maximum, the ceiling. For dislocation strengthening, there is always a maximum dislocation density that you can achieve, or you can't go beyond. Similar for precipitation strengthening. For grain boundary strengthening, the ceiling is the inverse hole patch effect when grain boundary sliding starts to operate. And similar for twin structure strengthening. All this effort put all our good effort together, we are able to push the strength of bulk materials from about 5% of the ideal to 14–15%. And by creating amorphous alloys, we are able to push that boundary a little bit higher to still no higher than 20% of the ideal strength. So in this sense, we have very much reached the end of the road by this approach. So the question is there a way around? Are there other roads possible? Are we able to overcome these limitations so that we can create materials of higher strengths? So to answer that question, we really need to understand how bulk materials fail. Right? You may think, yes, we have learned all this in fundamental physical metallurgy theory. We know them all. Indeed, we do. For example, we know the dislocation plasticity for ductile materials, crack formation propagation as a failure mode for brittle materials, and grain boundary sliding for nanocrystalline materials, and shear band sliding for amorphous materials. However, let's don't assume we know everything yet, but to take a fresh look at the situation. I give you on the left-hand side here a sample, let's say 100 millimeter in length. We apply a load and stretch the material only by 1 micron elongation, which corresponds to 0.001% of global strain, which is minimal, nothing. And yet, for plastic deformation matrix, one dislocation represents 100% local strain. So for a slip band of 100 dislocations, that's 10,000% local strain. So to produce this 0.01% global elongation in this sample, we will need 30 such slip bands. For a crack of a 1 nanometer opening, that corresponds to 300% local damage. A 1 micron crack, 300,000% local damage. For grain boundary sliding in nanocrystalline materials, we'll need 300 such slip size. Each measures 1,000% of local strain to produce 0.01%. 0.01% global strain. Same thing for the amorphous materials. So what do all these tell us? Summarizing them, and we know that bulk materials always fail by localized damages. And local damages are highly concentrated in magnitude. The damage concentration occurs by lattice strain transfer because we apply only very little uniformly, and yet they all seem to accumulate to a few sites with huge magnitudes. So the lattice strain transfer and the localization prevent the rest of the body to stretch further, thus to achieve higher strength. So it's very much like this, when we pull a rope, the rope always breaks at the weakest point when the rest of the rope is hardly used, made into good use. That's not ideal, but how can we prevent this? That's the question. Right. The thinking is that if only we could apply load, have many pairs of hands to apply load to every part of the material uniformly like this. So in this case, every part can be stretched to their maximum capacity. Even at a weaker point, this will not prevent others from achieving their ideal strength. Right. Or maybe we can stretch on every pair of atoms like this. Right. So that means we need to have millions of miniature instrument machines inside the material. And how can we achieve that without magic? In fact, we do have magic, and that is our Martensite transformation. We know that for stress-induced Martensite transformation here, when we apply a strain, global strain, that strain will be divided uniformly, equally, and distributed uniformly within the lattice. So in that sense, the Martensite transformation can be used as a divider, an equalizer, and a distributor of the applied strain to the atoms in the lattice. And by doing so, it prevents strain transfer and damage localization. Because every part has has an equal and a limited share of strain. You can't go beyond 10%. Also, as an atomic loader, which transfers and applies the external load directly onto each atom in the lattice placed adjacent to it. So this idea here invites us to design composites between a martensite metal, martensite transformation metal, as the tool, and the target metal in which we wish to induce the near ideal strains and strengths. Like this. But the question is, the thinking may be okay, but the question is, will this idea work? Well, let me show you a few examples as a proof of concept. Here's a nickel titanium niobium nanoribbon composite. This composite is produced by eutectic casting and then severe wire drawing to convert the laminar structure into these nanowires, nanoribbons of niobium. What we see here is a cross section. So the ribbons are thin and long. And these ribbons are able to exhibit an elastic strain of 6.7% upon tensile deformation when the matrix deforms by stress-induced Martensite transformation. And this is another one. If we say the niobium is a soft metal which has the ability not to break and deform to the high elastic strains, here is a brittle intermetallic compound of a titanium striate tin in a eutectic composite with nickel titanium. In this composite, the titanium striate tin is able to produce an elastic strain of 2%, which is 6 times higher than the maximum elastic strain than what we can achieve in bulk titanium striate tin. This is another example of composite of the same material. I mean, chemically uniform, composition-wise uniform, but it's a composite from a structural composite between amorphous and nanocrystalline nanodomains, crystalline nanodomains in this of nickel titanium ion. In this matrix, the transmission with the nanocrystalline region is able to help the amorphous matrix to achieve 5.9% elastic strain, which breaks the limit even theoretical prediction before this work. Well, these are, okay, there's one more here. This is a thin film, metallic thin film. We can deposit niobium, cobalt, nickel, palladium onto nickel titanium substrate. And by deforming the substrate in a pseudo-elastic manner, the film, which is not directly loaded by the external force, is able to deform elastically between -3 and -3.5% and +3.5% repeatedly and reversibly induced by the substrate. These are only a few examples, so we have done more. So basically show the proof of concept. So the conclusions here is not really conclusions because we have only one conclusion, that is this new concept may work. So what I give here is the logical steps of the thinking of this new concept. Hopefully you can take a snapshot and feel that through yourself. At the end, I also like to present, give here a list of our publications that serve to support my story today. Thank you very much. I'll stop here.